Hello. Hello.
Hi.
Hello.
Hello, good evening. Good evening. How are you doing?
Good evening.
How is everybody doing?
We are fine.
Oh, thank you. Okay, so far we have a few people online. We have 9 people. Let's say 8 because I have logged in twice. So should we wait for other people to join? Let's give them like 5 minutes. Or we should start.
Talk, let's start.
Okay. Oh. So last week we started with tissue processing. Can somebody remind us where we got to, please? Can somebody remind us where we got to on tissue processing the last time we met, last week? Those of you online, were you in the class last week? Please, you can unmute and answer the question. Is somebody there? Okay.
Everybody is here. I guess
Nobody was.
they don't want to talk.
Oh. This one, it should be interactive. Oh. If you don't talk, how would I know what I'm teaching you? You are getting it. Please talk, oh, so I will know that you are getting what I'm saying. Because this one, subsequently, I intend to make it not really like a lecture, but at least to give you some salient things because you are preparing for exam. So it will just be, it will be a lecture, but I will stress more on the points where you'll be expecting to answer questions from, so far as MCQs is concerned. Okay, so if nobody is talking, I assume we got to, let me share my screen. I'm not.
Please, madam, last week, most of us wasn't there. So, especially me, I just joined the group 2 days ago.
Oh, okay. So are you the one who has raised your hand, Fuseni?
Yes, please.
Oh, okay.
Okay, madam, we got to where you talked to us about the carousels and then the different types. We went further to discuss the manual processes where
so we were done with the manual and we went to automatic.
Okay, we deal with the manual process. We went into the automatic. That was when we ended the class.
Oh, okay.
And then you talk to us about the advantages and then how superior some of the machines are than the others.
Oh, okay, great. Okay, Latif, please, can you make me a host for the other one? I'm using I think I have a problem with my laptop with the audio part. So I'm using both my phone and my laptop. My phone is for the audio and my laptop is for the presentation. So if you can make me host for.
Okay, I'm seeing only one.
I see only one.
On the other one. Okay, I've seen the other one.
Uh-huh.
Okay, we are good to go.
Okay, thank you. Okay, so you said we passed this stage. Okay, yeah, yes, I think we did this one. Okay, so we were here, right? Were we here or we passed here?
We pass here, madam.
We
Okay.
passed there, madam.
Did we pass this one?
Yeah, we pass here
Yes,
too.
we passed here too.
Oh, okay, nice. Did we pass here too?
Yes, please.
Yes.
Oh, okay. Did we do this one?
Yeah, yeah, I think we were
Yes, we
around this place. The general overview.
General overview. Yeah, general consideration.
I think we passed it to madam. Yeah, we are good.
Okay, let's see. Okay, I don't remember I came this far. All right, so we were still on automatic processing. We were done with manual processing, and I said that automatic processing is done when there is a lot of samples. So you have a large number of samples coming in. You need to get automatic processor, and if there is a limited workforce, you need to get automatic processor, not limited workforce in a small sample size. So let's say you get like 10 cases in a day and there is only one histopathologist there or MLS there, you should get a automatic processor, no. But if the workload is so much, you are getting hundreds of cases a day and you need to process them, then you need to get automatic processor. Okay. And then I also mentioned to you that the disadvantage of automatic processor is a power. So if your power supply is not stable, then you cannot use automatic processor, or then you have to get a standby generator. Because when you start processing and then you get to a stage and the power goes off, that is where the sample will remain. And each of the fluids have effect on the tissue. They cause more hardening of the tissue. And so you would not want your one solution for a very long time. So I also mentioned to you that the automatic processor gives you the opportunity to set different timings for different sample, depends on the type of sample you are dealing with or how delicate the sample is. So you can have 4 hour sampling period, 6 hour, and then you can get as much as 18 hours. That is so far the maximum that can go, but depends on the type. If you are processing, like you are processing brain, maybe one sphere of the brain, or you are processing an organ, a whole gallbladder or a whole organ, you need more time, so you can go beyond that. And I also mentioned to you that for the automatic processing, you have the ability to also delay your processing. So let's say you are today is Friday, and usually pathology, unless there is an emergency or we don't run weekend duties, so you want to get your samples ready. The samples that have come on Friday, you want to get them ready by Monday. You can delay your processing. So you let the processor start on Sunday, and then by Monday morning, it will be ready for the subsequent procedures that needs to be done on the sample. So it makes work easier. It's not like the manual that you have to come back to work on Sunday to start the processing, and then all these time consuming and the stress and all that. Okay. And so it also enables rapid processing for very small biopsies like core biopsies, point biopsies, as I mentioned. Endoscopic biopsies, needle biopsies are also known as the core biopsies. Okay, so you can process within a very short time, within 4 hours, it should be done. And because of the presence of the heat, the temperature, and the vacuum in the automatic processor, it makes things easier. It reduces the turnaround time. Okay, and so you can vary the time, depends on the kind of sample or the type of sample that you are dealing with. That is an advantage of the automatic processor. And I mentioned to you that if you want penetration of the fluid into the tissue, you need to get the tissue at a thickness, an ideal thickness that will allow penetration of the tissue, to allow processing of the tissue to be efficient. Okay, so some people will go for between 3 to 5 millimeters in thickness of the section. So you get 3 to 5 millimeters thickness, and then the size of the width depends on the cassette that you are going to use, and the type of tissue that you are going to use, and the embedding modes that you are going to use. That will determine the size of the tissue. But the thickness should be between 3 to 5 millimeters. Some people will go as low as 2 millimeters, but ideally 3 to 5 millimeters is best, because when you trim and you get rid of all the excess tissue, you still get some left for your subsequent processing. So this is a processing schedule, short processing schedule for a very tiny biopsy. So like if you have needle biopsies where you have strands of tissue, like threads of tissue, the tissue is not thick so much that you want to spend so much time. I think the other time we mentioned that, so you can spend like 10 minutes in each of the reagents and you'll be fine to go, or good to go. So what are some of the advantages? As I mentioned earlier, you can customize your programs. So you can decide that, oh, for program 1 is going to be for core biopsies, or for tiny biopsies, or for this kind of biopsies. Program 2 is for fibroids. So program 3 is for any other tissue. You can just customize your program. So when you go in there, you know that program 1 is for this. So if the samples are all, so then you can group your samples. So as it comes, you group them as to which ones are medium-sized sample, large size sample, and the small size sample, so that you know that this is a program for the small size samples, where you use about 15 minutes for the processing in each of the reagents. Okay, and then the medium size, where you use like 1 hour, and then the large size, where you use like 1.5 hours or 2 hours in a solution. Okay, so you can schedule that, and it is rapid. You can set delays, as I've mentioned to you. There is less contamination. There is less contamination, especially with the fluid transfer or the self-contained. Everything is inside, and so hardly will you get contamination, spillages and fumes and other things. You won't get. So you enter a lab that uses self-contained, and you hardly smell of any chemical or any reagents there, and it makes the environment very friendly and safe for the worker who is there. So I also mentioned to you that one of the ways of processing sample in a fast way is the use of microwave. So you can use microwave oven to process samples. But now there is also an automatic processor that uses microwave. That is the constant throughput. Okay, constant throughput or continuous throughput processing, where you use microwave. Okay, you use microwave in the processor. And so because of the microwave, because of the heat, it fastens the processing period. And it also allows penetration, easy penetration. But the disadvantage is that if you don't set your timings well, after the processing, you realize that your tissue is bent or is fried or it cannot be used for anything. Okay, so when you are using constant throughput processing, you need to be sure that your your timings are set properly and they are regularly checked in order not to cause damage to your processing. Okay. So for normal processing without the microwave, you use formalin, you use alcohol, you use xylene, you use all the reagents. But for the microwave type, okay, you use isopropanol, you don't use formalin, you don't use xylene because it will create what? It can explode. Okay, especially the xylene, it can catch fire and it can explode. So you use simple reagents that cannot catch fire. Okay. So this is a processing schedule for normal farm pouring. So as I mentioned to you, the timing will vary, depends on how many solutions that you have. The more solutions you have for one reagent, the less time you spend in it. But the less solutions you have, so let's say if you have 2 alcohols, you spend more time in the alcohol than if you have 4 alcohols or 5 alcohols. Okay, so all these things come into play to influence the timings within the reagent. So if you have xylene, if you have 1 xylene or 2 xylenes, you spend more time, depends on the size of the tissue. But if you have 5 or 6, then it means that you reduce the time, depends on the type of tissue that you are dealing with. So this one is a microwave one, that is the constant throughput or continuous throughput. However, usually it's constant throughput. So usually we call it constant throughput, but some people may want to use continuous throughput for this one. So that is why you have the microwave in it. And as I've mentioned, you don't use flammables. You don't use materials that are, so you don't use ethanol. Ethanol is very flammable. You don't use xylene. Okay, you don't use formalin because it will create a lot of fumes, and the formalin vapor is not good. So you don't use that one. So you use isopropanol, acetic acid, use polyethylene glycol, and all these ones. Simple reagents that does not cause explosion or catch fire when you are using. So what are some of the advantages? It produces quality H&E stain, or it produces quality histological stains, because you are not using any fixative that will cause coagulation of the cells or coagulation of proteins that will cause denaturing of the proteins, but it is heat. Okay, so you are able to get the architecture of the tissue better compared to the other methods. Okay, and then you are able to preserve the DNA or the macromolecules, RNA, and all those ones. When you use formalin, they also have their effect on it. They can cause some form of degradation. And so if you want to extract macromolecules like DNA, RNA, proteins, and those things, the microwave method is the best. Okay, the microwave method is the, because it doesn't have any impact on these materials, and then also preserves the quality of the tissue well. So how do you ensure that your lab is free of xylene? So somebody will ask you, oh, you are working in a pathology lab, you are exposed to xylene. Xylene is one of the major reagents that you use in the lab, apart from the fact that you are using constant throughput machine, which is not common. It is not a common equipment that is a lot of people use. And so you'll be using normal tissue processing. So how do you prevent the presence or the smell of xylene or spillage of xylene because xylene is a cancerous agent. It's a very dangerous agent. It can cause so much. It can cause nervous impairment, and it can cause a lot of pathologies to the individual user. So you have to be sure that your lab is always clear of xylene. Okay. And so there are other alternatives that you can use apart from the xylene. There are other alternatives that you can use. So I mentioned to you that you can use some oils. Last week I mentioned to you, you can use some oils. You can use citrus oil. You can use fruit, vegetable oil. You can use other form. You can also use chloroform. Okay, you can also use chloroform as an alternative to xylene. Even though chloroform too has its own any of them. So this is about how to clean them. Microtome, or how to clean your microtome. The main materials that you use, where you have, especially you have a wax being there. So what do you do? What do you use to clean? So if you can use any alcohol to clean, but if you have wax in there, then you have to use what xylene to clean, because the xylene will what melt the wax. So you use xylene to there. Okay, so that is all you. So what do you do when there is a mix-up in the pathology lab? Let's say the you are embedding, and then you have put a lot of cassettes on the embedding center, and then you have opened them. That is a bad habit that a lot of people, some people get themselves involved because they want to do the thing fast track. So they take cassettes and they open a lot of cassettes, and then they try to be fast. By the time you realize they are mixed up. So what do you do when there is a mixed up? One of the things you do is to look at the request form. Okay, take the request form, look at the details on the request form, look at the grossing information. When the sample was being grossed, like when the sample was being examined, the descriptions that were given about the sample, you use that to check whether it is it correlates with what you are seeing. Okay, and then you can also use the site where the sample is coming from. And so when you look at the architecture of the tissue or the cells that are present, you'll be able to tell that, oh, this is a kidney, this is liver, this is the gallbladder, this is stomach, this is fibroid, this is that. And so you look at the request form, and is it fibroid or is it, what is it? So you need all this information to be able to identify which tissue is present, okay, or which tissue has been mixed up. Any questions? Any questions? Any questions? Hussein, your hand is still up. Or if you are not asking a question, please can you bring your hand down? Any questions so far? So now we are finished with tissue processing. So I mentioned to you that tissue processing, there are only 3 steps. Okay, so you have dehydration, you have clearing, and then you have what? Infiltration. Fixation is not part of tissue processing, and embedding too is not part of tissue processing. Okay, so when you talk about tissue processing, you're talking about dehydration, you're talking about clearing, and you're talking about infiltration. Okay, so after the tissue has been infiltrated and then processing has been done depending on the type of tissue, the type of sample that you are dealing with. You embed. So if you use the normal formalin fixed samples, you embed. Okay, but if you are using frozen section, then the ice will produce the block, the embedding. It will be the embedding medium. Okay, the ice will be the embedding medium that will hold the tissue firm. But if you are using formalin fixed tissues, then you embed in what? Paraffin wax. Okay, paraffin wax. And I mentioned to you earlier that depending on the type of tissue that you have, how soft, how hard the tissue is, there are several types of embedding media that you can use. So when we're talking about infiltrating media, we spoke about infiltrating media, as I mentioned to you, is the same medium that you use for what? Embedding. Okay, so if you use, which is commonly, the common one that is used is the paraffin. Okay, so you can modify the paraffin depending on the nature of the sample that you are using. If the sample is softer than the paraffin, then it means that you have to add softening material to the paraffin. So I mentioned some of them. I mentioned agar, I mentioned sericin, I mentioned stearic acid, I mentioned some of them. And then if the tissue is also harder than the paraffin wax, then you can use resin, you can use plastic, you can use rubber, you can use materials that will also harden the wax, so that it will have what? Good consistency between the tissue and then the wax. Okay, so embedding, as we all know, is a supporting medium to make the sample solid for sectioning. So you embed to enable what? Sectioning. So what do you need for embedding? So usually you have an embedding center which has a cold plate, it has a warm plate. Okay, so the cold plate is where you freeze, or you set your the molten wax. So that is where you allow the molten wax to set. Okay, the hot plate, you have two components. One is for the tissue, and then one part is for the embedding molds. Okay, for the embedding mold. So I mentioned to you that the embedding molds, there are several. Initially, it was wooden that was being used. So the wooden, we had the 2 L's. So the 2L, you have a wooden that is L shape. And so depending on the size of the tissue, you can manipulate the L to become smaller, or you can manipulate it to become what? Bigger. Okay. Then after the wooden type, metals also came in. So you have L-shaped metals. So you can have various sizes from the same 2L shape. Okay, so you can make it, I think I have, let me see. So this is the L shape. So you have 2 L's. So this is one. Let me use it. So this is 2 L's. This is 1 L, and this is another L. You can see it better here. This is 1 L. This is a 1 L. This is the metal embedding mold, and this is the wooden one. Okay, so you can make it bigger or you can make it smaller, depends on the size of tissue that you have. Okay, so you can use the same embedding mold for several shapes. Okay, then it graduated from the L shapes to these molds, where you also is metal, non-stick metals, okay, or steel molds. Okay, so that one too, you have different shapes and sizes. Okay, so you have the smallest one, and then you have a bigger one. So if you are using if you, for example, you want to embed a whole eye, you get the mold is bigger than this, should be able to carry the whole eye. Okay, so the mold will be bigger than this one. So these are the routine sizes that are used in the lab. Okay, this is also plastic ones that are used, plastic embedding molds that are used, which is not very common. The most common ones are the metal one. So what do you need when you are going to embed a tissue? Okay, so you need your molten wax. And as I mentioned to you, the wax has to be what? in a molten state. Okay, so it has to be a temperature of about 3 to 5 degrees higher than the melting point of the wax, so that it will still be fluid. Okay, and it can be able to penetrate the tissue even though after infiltration, so that it can have fine settings, uniform or homogeneous solidity. Okay, so when it solidifies, it will give you a homogeneous. But if it is not very fluid and it solidifies, it can give you some form of crystallization, some hardness, and some softness part. So you have to make sure that it is fluid. Okay, so you have that one, and then you have your mold, your embedding mold. So you have the very varied sizes of the embedding. If you are using the wood, the L-shaped ones, then you form your own size, depends on the size of the tissue. But if you're using the already sized embedding molds, like the metal ones I just showed you, then you pick the ones that will be convenient for the samples that you are going to embed. Then you need forceps. Okay, you need forceps, and then you need your cold plate. So let's say you don't have embedding center, but you are using manual embedding. You have to get your ice block, then you have to get your hot plate. Okay, where you have your wax being melted, or the wax on the cassette, or on the embedding mold melting away, so that you can reuse them as and when it becomes necessary. So if you take the embedding center, it has as I mentioned, it has a cold plate, it has a warm plate, and then you have the chamber which contains the paraffin, the molten paraffin. So you have a chamber at the top, open chamber where you put the crystals or the chunk of wax in there, and then it melts. And then it has a dispenser at the bottom. At the lower part, you have a dispenser. So the dispenser has a probe there. That's where the molten wax passes. So there is something there that you press. Let me see if there is. Okay. So this is an embedding center. So you have the cold plate. This is the cold plate. This is the warm plate, and then the wax bath is up here. Okay. So these ones, they have 3 chambers of the wax bath. Okay. So one may be for tissue that is not yet embedded, and then you have one for the one that is going to be used for the embedding. Okay, so this is what you press. Some of them, this one is at the back here. It's a metal at the back here. So you press on it and then it will dispense. This one, it is in front. So this is the probe. The probe is here. So when you press this one, it will dispense the wax by it's the molten wax by itself. And then you put it in the mold, you add your tissue, then you place it on the cold plate. Then you attack. So usually you keep your the molds here so that you can easily have access to them. So this is what you get after embedding. So you get your mold with your cassette. So the cassette is only the cover that you remove, but the base that contains the tissue is what you have labeled with the patient's identity or number. Okay, so that cassette goes with the sample until it is stored. Okay, so you use that to do the embedding. Okay, and other things that you consider during embedding is orientation of the tissue. Very, very important. Orientation of the tissue. So apart from getting your embedding center, if you don't have, getting your hot plate, your cold plate, get is the orientation of the tissue. Very, very important. If you don't orient the tissue well, you cut the tissue in a tissue that has layers of epithelium, layers of cells, layers of epithelium. Like if you take, let's say, And so you need to make sure that as you're cutting all the layers. Okay, you don't orient it in such a way that it is only one layer that is seen. Dealing with, okay, especially if it is malignant. Okay, you want to know how deep the tissue has gone, the tumor has gone into the tissue. So you need to get all. Okay, the same thing if you are dealing with appendix, you are dealing with fallopian tube, those tubular structures, or even stomach, you are dealing with those hollow organs. You have to make sure that you embed on edge. So you embed with the layers in the mold. So you embed with the layers in the mold so that when you cut, you will see all the layers. Okay. But if you have a tissue that is, it doesn't have any layers, like you have something like a liver, you have something like lung, you have something like spleen, you have something like fibroids, you have something like what, those kind of tissue, as you can see, you embed them flat. So you embed them at the flattest plane of the tissue, the most flattest plane of the tissue, depending on how deep the embedding mode you are using is. Okay, so because I mentioned to you that the thickness of the sample should be what, 3 to 5 millimeters. Okay, and so it will be thin, but the other sizes, maybe the length and then the breadth may be longer than the width. Okay, may be longer than the width or the thickness. Okay, and so depending on how deep your mold is, then you can align them per the flattest part of the tissue. Okay, but the other tubular ones or epithelial surfaces, tissue that have epithelial surfaces, you embed it on edge. Okay, so you embed it in such a way that you can see all the layers. Okay, you don't embed flat. Okay, so orientation is very important. So sometimes from the theater, they will label the tissue that you should embed at this side. So they will put either a thread or a color or something to indicate that you should embed at this side of the tissue. Okay, so they can give you an indication. If they don't give you an indication, then the person who does the grossing would give an indication that this tissue will have to be embedded on edge or it has to be embedded on flat. Okay, so some of the tissue like uterus, you have to embed both flat and then at the edge. Okay, because it also has layers. Okay, if you take appendix, you embed flat and on edge because you want to know if the tissue is just in the mucosa or it has gone deep into the tissue. The tumor is just in the mucosa or it has gone deep into the tissue. So you have the flat one and then you have the one on edge where you see the layers. Okay. If you have any question, please prompt me and let me explain it to you. Okay. So if you have a tissue that is long, the length is too long, and then when you put it in a vertical or in a horizontal way, it cannot fit into the embedding mode. You can embed it diagonally. Okay, but usually it is not advisable that a tissue is cut longer than the length of the embedding mode. But in case it happens, then that's what you do. Or you divide it into two, or you divide the tissue into two, and then it can fit into the embedding mode. Okay, so these ones I have mentioned them already. So this is example sketch showing the tissue orientation. Okay, so this one, if the tissue is longer than the embedding mode, then you embed it diagonally. Okay, so if you have something like skin, you have to embed it on the edge. So you embed it. I don't even know how to mention embed on edge. So let's say Okay, let's say you have an exercise book. Okay, exercise book or notebook, it has layers. And so you want to see the different book leaves that are inside. You embed it with a side, okay, where you can read the papers, where you can count them. Okay, so that is what you embed. That is the embed on edge. Okay, and then when you put the book flat on the bed on the table, that is embedding flat. So you see only one surface. But if you use the side, you see what all the layers of the different leaves that are in the tissue. Okay, that is what I mean by embed on flat and then embed edge on edge. Okay. So this is a tubular organ or tissue that you embed on edge. So this one has been embedded on edge and this one has been embedded flat. Okay, so you can see the flat if it is just in the one layer or it has gone beyond. If it has gone beyond, then the layers, then the embed on edge will be seen, and this is embed flat. Okay. And then if you have multiple tissue, you have to arrange them in such a way that you don't have to scatter them. If you scatter them because the embedding mode is big, so you are scattering them, it makes examination very difficult. So you arrange them in such a way that each of the smaller biopsies stands alone. They are not hindered by, they are not lying on each other. So they stand alone, but they follow each other nicely. So when you start looking at it on the microscope, you can look in a direction, not that you look here and then you have to go and be looking for another one somewhere and be looking for another. It shouldn't be scattered all over. It has to be arranged nicely like this or this way or diagonally. So far as they are following each other and each of them are isolated, they are not so overlapping, then you're good to go. So this part, I think we have mentioned them already somewhere during the infiltrating medium. So it's the same thing. You can use resins, alternative embedding medium. You can use resin, you can use agar. And I mentioned to you that you are embedding what tissue for electron microscopy, where you need very thin sections, very thin, less than a micron. You need hard tissue to be able to do that. So you use resins. And if the tissue is soft, if the tissue is very soft tissue, you use agar. I've mentioned that gelatin, celluloidine, and all that. Low viscosity nitrocellulose, we are all embedding media you can use. Depends on what the type of tissue that you are dealing. You have extra wax, then you have water soluble wax. So the water soluble waxes usually are used for frozen sections. So frozen sections are sections that you don't go to the formalin. You don't use formalin to preserve them. So you freeze the samples. So you can use water soluble waxes like glycerin, glycerol, and all those. And then there are also situations where you do double embedding, especially if you have used agar or you have used celluloidine or you have used gelatin. Okay, nitrocellulose, you have used those soft ones, and then you want to embed them in a solid medium. So you use the agar, and then you embed them in paraffin again, or you use agar, then you embed them in low viscosity nitrocellulose, or you want to embed them in celluloidine or any other. It depends on the hardness of it. Okay, so these are all double embedding media. Sorry. So you have agar and paraffin as embedded, nitrocellulose and paraffin. You have ester wax and agar and all that. So any questions about embedding?
Yeah, madam.
Yes, dear.
Please, with a double embedding.
Yes,
Yeah, please, I would like to know with a double embedding, what to happen before you have to do the double embedding with the tissue.
Yeah, so let's say you have a very soft tissue. Okay, you have very soft friable tissue, like you have a brain or tissue that is very soft, like fatty tissues, very soft tissue. It will be very difficult for you to embed it straight away in a medium that is hard, like paraffin. Okay, so first you embed it in a medium that has a consistency similar to the tissue. So you embed it in either agar or in a nitrocellulose. Those ones are very soft embedding media. Okay, so you embed it in that one to make it a bit solid before you transfer it into wax. So you embed it in it, it forms like a tissue. Okay, so when we get to cytology, we'll talk about cell blocking. So where you block the cells. So usually you can also use agar to block the cell, especially if you have single cells. You put them together, you want to preserve them like tissue. Okay, so you put them together, you put it in an agar because they are fragile, they are single cell. So you put them in agar, the agar solidifies, and that is treated as a tissue. Okay, then after that, it is sent into paraffin, and then it is blocked with what? It is embedded in paraffin wax. Do you get what I'm saying?
Yes, madam, I'm listening to you.
So are you clear now, or you want more explanation?
Yes, please. Yes, please. I'm okay. Thank you.
Yeah, okay.
Yes, please.
Okay. So that is what happens. So you go through the tissue processing. You can do the first blocking before you start the tissue processing. Okay, or you can do the tissue processing and then after that you do it inside. But usually it is advisable that you do the first blocking first. So before the tissue goes through all these other reagents, and then it is finally embedded in wax. Any more questions on tissue processing and embedding? Any more? Okay. So let me. So let me go to staining. You didn't, nobody spoke about, or you want me to talk about microtomy? Do you want me to talk about microtomy? Because nobody raised issue about microtomy. So I believe you are fine with microtomy. Should we go on with the staining? Okay, so I think
Madam,
we can
let's
go
go
on.
on. Let's go on.
Madam, please,
Okay.
madam, let's go on. Please, let's go on.
Okay. So staining. So anything that it has color means that it has been stained. It can be a cloth, it can be material, it can be anything. It can be plastic material. Stain can have effect on the material that the dye is going to be impacted on. There should be an interaction between. Okay, that is why sometimes in water and then it is faded, or the color just how do we call it? It diffuses into the whole material and it pulses. It means that the interaction between the dye and the material was not good. So it couldn't keep the material to itself. Okay, it couldn't keep the material to itself. And so it diffuses out when there is another medium that is introduced. So the same principle also applies to histological samples. Okay, so any sample that comes depends on whether it's going to be routine H&E or it's going to be special stain or it's going to be even immunohistochemistry or immunofluorescence. There has to be some interaction. Okay, there has to be some interaction between the tissue and what you are going to introduce to produce the color. Okay, there should be some interaction. So you have the dye and then the substrate or the tissue that you need to do. Okay. So what do we use the staining for? We use the staining to label the tissue. So when you apply a stain to a tissue, it means that you want to label that tissue for specific identification or specific evaluation. So if let's say you want to impart green color, yes, you think that the green color will produce better contrast or better vision. It will be nicer compared to other colors. Okay, so that is what it is done. Okay, so what happens? So I mentioned to you that you have a tissue. So you have a tissue that needs to be stained, and then you have a color component. Okay, so the tissue and then the color component comes together to produce a isochrome. So you have the chemical component. You have the chemical component of the color of the dye, and then you have the color producing part. So the color producing part, and then the material that is the dye. Because when you take a dye, it is not just the color. The color has a material. It's either powder or it's either what fluid. Okay, that you mix to get your this thing. Okay, so the coloring part and then the component that becomes the dye forms together to form what you call the isochrome. I hope you are getting what I'm saying. So the staining, the color component is the chromophore, and then you have the material that has the chromophore. Okay, so you put the two together to form what? The isochrome. So it is the isochrome that is the dye that will impact what? The color that you leave on the material. Okay. And then there are also some dyes or some stains that do not directly impact color. Okay, they do not directly impact color. Like some people, when they see a young lady or a young man, they are interested in the person, they have to go through somebody before they get to the person. So they have betweeners. Okay, in staining too, there is something like that. They are also betweeners inside. Okay, so you have the betweeners are called what? Mordants. Okay, mordant. So when you come to our normal H&E stain, we have what we call mordant. So histology, our stain, our H&E stain has a mordant because the H&E itself cannot impact a color that is, it creates much contrast that you can be able to identify and say that this is the nucleus of the cell, especially the hematoxin. Okay, and so it has what? A mordant, and it's a mordant that does what? The coloring that's introduced makes the nucleus bright. Okay, so when it comes to, we'll go into details about that when we talk about hematoxins. Okay. So you have the chromogen, which is the one that is producing the color. You have the substrate, that is the tissue, and within the the two of them depends on the type of dye that you are using. Some of them you can use them separately. So you can use the color part, and then you introduce the mordant, and then you add the substrate to it, and then it works. Sometimes you add the mordant to the chromophore, and then it forms the isochrome, and then you add it to the substrate and you produce color. Okay. So what happens that there is that interaction between the dye and then the tissue? What happens between the two components that produce the color? So these are attractions that happens between the two components, either the dye or the tissue. There should be something, there should be some like poles, there should be something that attracts, just like friendship. Before you become a friend to somebody, something attracts you to the person. Some people, it is the eye of the person. Some people, it's the shape of the person. Some people, it's the color of the person. Anything that attracts you to somebody is the same thing that happens in staining. Okay, so between the tissue that is going to be stained and then the dye or the stain that is going to impact the color, there should be some interaction. Okay, and this interaction are involved in several mechanisms, okay, that causes it. So some of them are what is here. We have the electrostatic bonding. Okay, electrostatic bonding where electrons are exchanged, positive and negative. And then you have what? Hydrogen bonding, where hydrogen ions are exchanged. Okay, so some will have excess hydrogen ion and donate it to one that doesn't have, and then it causes a linkage between them. And then we have van der Waals forces. These are weak attractive forces. Okay, weak attractive forces that also causes them to come together. Okay, then you have covalent bonding, you have hydrophobic bonding. Okay, you have di aggregation. So the di aggregates and then settles on top, okay, of the tissue and produces color. Okay, and then you have the ability of the tissue to be permeable to the dye. Okay, so if the tissue allows the dye to permeate it, it is also a mechanism that it uses to stain the dye. Okay, so these are some of the mechanisms of staining. Very important MCQs. Okay, so they can list them, several mechanisms and say which of these mechanisms can be applied to staining. So it is through the hydrostatic bonding that you have dyes, that you have acidic dyes and then you have basic dyes. So you have positive charge and negative charge, as I mentioned to you. So negative charge is for acidic dyes and positive charge is for what? Basic dye. So in a natural sense, acidic dye will stain basic component, and then the basic dye will stain what? Acidic component of the tissue. But this rule doesn't really work so far as histology staining is concerned, especially H&E. Okay, H&E, it is not acid to acid. It is not acid to basic, but it is acid to acid. We'll go into details about it as we go along. So these are just classification of dyes using what? Electrostatic bonding. So you have cationic dye, anionic dye, or you have what? Acidic dye, basic dye. Okay, and all that. So as I mentioned to you, positive and negative. Negative means that it needs, okay, and then positive means that it can give to you. Okay, it can give to the negative. Negative, oh, it doesn't have, so it will accept. Okay, and all these depends on what? pH. The pH of the dye also influences whether it is what? Acidic or it is what? Basic. Okay. So when we come to our normal, when it comes to our normal H&E staining, which is the routine stain that we use in the hematoxylin, H&E is hematoxylin and eosin. Okay, so hematoxylin stains the nuclear component. Okay, so it stains the nuclear component, it stains the DNA, it stains the nucleus. Okay, and then the eosin stains the cytoplasmic component. Okay, so usually we say the hematoxylin stains the DNA because DNA is found in the nucleus. RNA is produced in the nucleus, but it is released into the cytoplasm. Okay, RNA doesn't stay in the nucleus. So when you stain the nucleus, you are not staining RNA, you are staining the DNA. Okay, but when it is in the cytoplasm, then you are staining RNA and the other organelles and other materials that are in the cytoplasm. But when it comes to the nucleus, it is what? DNA. Okay, it's the DNA that you are staining. Or how do you call it? Chromosomes. The chromosomes have the DNA on them. Okay, great. So what is hematoxylin and eosin stain? As I've mentioned to you, hematoxylin is a nuclear stain, and then the eosin is the cytoplasmic stain, and it's the most widely used routine stain in pathology. Okay, in pathology, especially histopathology. Okay, that's the most widely used stain. So I've mentioned to you what it stains. So it stains the nucleus, blue black, and then it stains what the eosin stains the cytoplasm shades of pink, depends on the intensity of the material that occupy both the nucleus and the cell. So if the nuclear content is so much, you have a lot of DNA, it will stain darker. The more darker it stays. That's why you have what hyperchromasia when you are talking about malignancy, because in malignancy you have a lot of DNA material because the cells are multiplying, so they need to get more to be able to multiply. So the nucleus becomes hyperchromatic, it becomes densely stained because the content has increased in size. Okay, and then the cytoplasm also varies, depends on the content, how much RNA is in there, how much organelles are in there, how much components are released in there. Okay, and then the surrounding tissues. Okay, the surrounding tissue, the connective tissue. Okay, the mucosa, the connective tissue also will depict whether the pinkish nature of the surrounding tissue will have what varied intensity. Okay, depends on the content. The more tissue fibers in there, it will stain more pink. If you have less, it will stain what less. So when you stain H&E and this, the connective tissue is staining more pink, and then you see that the pink is allocated to some portions of the connective tissue, then you should know that there is what some inclusion, some materials in there that needs to be demonstrated. So from the clinical summary and from the histology that you have done, you'll be able to know which special stain to do to be able to identify what is found in a tissue that's staining more pink than is. So you know of hematoxylin already, that it is from a wood, a log wood, and then they extract it by putting it in water, boiling it, and then getting the, just like you prepare a local stem of a tree, you cut it into pieces, you put it in water, you boil it. Some of them you don't boil, you put it in water. Some of them you use alcohol, you put in alcohol, bitters, then it releases the content into the alcohol, and you drink, and then whatever you get out of it, you get. So the same thing with hematoxylin. Okay. But one thing about hematoxylin is that the hematoxylin itself does not have any color. Okay. So what it does, what is done to the hematoxylin is that it is oxidized. Okay. So it is oxidized to become hematine. So it is the hematine that produces the color. Okay. And the oxidation can be done naturally or chemically or artificially. Okay. So you can use the natural means where you use the sunlight. So after preparing your hematoxylin stain, you expose it to sunlight. Okay. And then that's the natural means. And then you have the artificial means where you use what chemical. So usually you use what potassium permanganate. Okay. You can use that's why there are several ripening agents that you can use. Okay, so as I mentioned, the chemical you use, potassium permanganate, that is the frequent ones that are being used. Okay, and then the natural, as I mentioned, you expose it to the sun, and then the sun. Sometimes you can use the hematoxylin without ripening, which is not very commonly used. Maybe in special occasions that they can be used, but it doesn't produce the staining quality that is needed because there is no oxidation. Okay. So this is the conversion of hematoxylin to hematine, and all that's not all that you need is that the conversion is done by what oxidation, and the oxidation can be natural, or it can be synthetic, or it can be chemical. Okay, so natural is when you expose it to the sun, or you expose it to the air, the sunlight and the air, and then it oxidizes it. Or the chemical you add what potassium permanganate. Okay, but it depends on the type of hematoxylin that you are also using. The ripening agents also differ. Okay, some of them will use mercuric oxide, some of them will use mercuric chloride, some of them will use sodium iodate, some of them will use potassium permanganate. Depends on the the type of hematoxylin that you are preparing. Okay, that's why we have several types of hematoxylin. Okay, so I think. So here is our two examples. So you have LH hematoxylin, which uses what? Sodium iodate. And then you have Delafield's hematoxylin, which uses what? Mercury chloride. Okay, all is done to what? Increase the dye content of the stain. Okay, to increase the dye content of the stain. So the more the chemicals stay, especially if you are using the chemical or artificial ripening, the more you expose it to the reagent, the more it oxidizes. Okay, so sometimes you, when you add it, you mix it up, you filter, and then some of this thing moves away, or you can prevent the over oxidation by adding glycerol to the reagent. Okay, and for the natural one, it means that when you ripen, the more it stays in the sun, or in the sun, that is, the more it ripens. So if it ripens and then you think that that's ripened enough, you don't just put it in the sun, you just keep it under in a wardrobe, or where there is no exposure to sunlight. And I also mentioned to you that for hematoxylin, it does not have a color that is so much distinguishable. It doesn't produce that contrast, very good contrast, so far as the cytoplasmic stain is concerned. And so there is a need to add a mordant. Okay, there's a need to add a mordant to it. Just like somebody who is going to corner a girl, the person goes and the person is standing there, the person doesn't know what to say, the person will just be talking about unnecessary things, when the person has to go straight ahead and say what the person wants to say. Okay, so the person is not able to talk, so the person goes to somebody and say, oh, I saw this girl, I saw this boy, I'm interested, can you do something for me? Then the person will go and do. Okay, so the same thing, the hematoxylin too, even though can impact some color, but the color is not so distinct. It doesn't produce that bright contrast, that sharp contrast between the cell. And so you need to introduce a mordant that will create that contrast between the dye and then the tissue. So it forms something like a bridge between the dye and the tissue. Okay, it forms something like a bridge between the dye and the tissue. So as I mentioned, it has poor affinity for the tissue, so it doesn't cause, so the link becomes weak, so it doesn't produce any sharp contrast. Okay, and so you need to add mordants. Okay, so the mordants are usually metals. Okay, they are metal salts. Okay, so it depends on which type of metal that you usually use. Trivalent metal, that's +2 or +3 metals. Okay, +2 or +3 metals. And so salts, +2 or +3 metal salt. That is, divalent is +2, and then trivalent is what? +3 salt. Okay, and depends on the metal that is used, then you have the mordants, the name of the mordant. So if you use aluminum, aluminum has how many valence?
That's 3.
Is 3. So aluminum is 3+. Okay, so aluminum is 3+. So you have what? Aluminum mordants. Okay, so you have alum mordants or alum. We have iron. We have phosphotungsten. We have lead. We have molybdenum. We have a lot of them. Depends on what you are going to use. But usually, apart from the alum hematoxylin, the rest are used for special cases. Okay, the rest are used for special cases. It's only the alum that is used routinely in our routine labs. But for the iron mordant, we talk about them as we go along. Okay. So it forms a covalent bond between the metals and then the dyes. Okay, so there is an interaction between them that produces a color that is produce enough contrast between the tissue and then the model. Okay, so as I mentioned, we have aluminum salt, that is the alum mordant. So usually when you're using alum as the mordant, you called what? Alum hematoxin. If it is iron, it is what? Iron hematoxin. If it is tungsten, it is tungsten hematoxin. If it's lead, if it's molybdenum, they are all what? Mordants. They are all trivalent or what? Divalent metals that are used as mordant, pasting what? The interaction between the dye and the what? The tissue. Okay, to produce what? A bright contrast between the tissue and the dye. Okay. So as I mentioned, it forms a lake or a bridge between the tissue and the dye. So I've mentioned this before, that based on the mordant used, you have different types of hematoxins that are available. So when you take alum hematoxin, and the alum hematoxin too, you have several of them. Depends on who, just a small manipulations that they have done. Okay, you know, wise people, they can do manipulation. Ghanaians or Africans, if somebody does something and then you want to do a similar thing, what they do is they kill the person and then they can keep the person's face. But a white person will maintain the old one and just add something small to it, and then we give it another name. It is there. If you like, buy. If you don't like, don't buy. Okay. But Ghanaians, we will spoil it. If it is not for us, it shouldn't be for anybody. Like people, those days when we were producing matches in Ghana, they were producing these matches with the blue box. And because somebody is envious or whatever, the person went to do so many things about the matches, went to pour water on the matches, and then when the matches came to the market, you spark the matches, it doesn't spark, it doesn't ignite, it doesn't set, it doesn't inflame, doesn't do anything. And now that matches is no more used in Ghana, it's not produced. So everything is important because it is not for me, so it shouldn't be for anybody. Okay, that's Ghanaian mentality. But the white people are not like that. These are the same hematoxin, but they have made small modification that depends on the individual using it, your preference. Then you can go in for any of them. Okay, so we have LH hematoxin, you have Meyers hematoxin, you have Gales hematoxin, you have Harris hematoxin, you have Coles hematoxin, you have Delafield's hematoxin, you have Karazi. They are all alum hematoxin. Okay, but when you stain, the characteristics of the staining property will influence your choice of the food. Okay, so for HNE, normal HNE, the best one that is used is Harris hematoxin. But if you don't have Harris hematoxin, you can use Meyers hematoxin. Now, a lot more people are using Meyers than Harris hematoxin because that is the one that is available. Okay. In cytology, we use more of Gale's hematoxin. Okay. We also use hematoxin in cytology. So we use more of Gale's hematoxin. But if you don't get Gale's hematoxin, we use Harris or Meyers hematoxin. So it depends on the preference of the technologist or the scientist in charge, the pathologist in relation to the pathologist, and they decide on which hematoxin will give the brightest contrast between them. So for alum hematoxin, it is used progressively or it can be used regressively. If you say progressive, it means that you stain it within specific time. So you first several sections of the same kind at different times. So if you, let's say you take liver and produce several sections of the liver, okay, then you stain it within specific time. So let's say you stain it for 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes, 7. So you stain it within specific time. And then the one that nuclear staining characteristics is the type that you stick to. Okay, so you, for that hematoxin, you stain for that specific minute, it gives you stain it progressively for what? That time, predetermined time, that 5 minutes and 5 minutes. You only change the time when you have used the stain for a very long time. You have used this several to stain several tissue. You know, the more you stain, the less the property, the staining quality. Okay, so you increase the time. Or how fresh the tissue, how fresh the stain, if the stain is freshly prepared, or it has been ripened, it has been there for a very long time, that one too, it alters the time. Okay, it also alters the time, because you can't compare the staining quality of a stain that has not been used before to a stain that has been used for hundreds and hundreds of tissue or hundreds of sections. Okay, that varies the time. But for the regressive, you can stain it longer. You can stain it overnight. You can stain it as long as you want, but you will decolorize or you will differentiate. Okay, you have to remove the excess stain that you have impacted by staining for a very long time. So that one, it doesn't have predetermined time. It doesn't have limited time. You stain it as and when you want to stain, as and when you'll be available to attend to it. And then you differentiate by using what? Acid alcohol. Okay, so you use HCl, 0.5 to 1% HCl to do what? The decolorization. Okay, and then after, either you choose the progressive or you choose the regressive. After that, you have to make sure that the mordant that you have put into the dye plays its role, and the role that the mordant plays is in connection with what we call the bluing. Okay, so you have to blue. That is why the nucleus is what? Blue black. So the more you blue it, the darker it becomes. That's why it has shades of blue and black. Okay, so if you blue it for a very long time, it will become darkened, and then become more black or bluish black. Okay, or blue black. Okay, but ideally it's supposed to be blue. Okay, but if you blue it for a longer time, it means that the reaction is going to go on several, and then the color becomes what? More darker. Okay, so it is the mordant that influences the bluing. Okay, mordant that influences the bluing. That is alum epoxy that we are talking about. So what happens? So I mentioned to you that if you overstain, you use what? An HCl. I've mentioned that. So what happens during bluing? Please, if you have any question, let me know. What happens during bluing? So I mentioned to you that the alum matoxin, it uses what? Aluminium salt. Okay, so the aluminium salt can be aluminium sulfate or aluminium phosphate. Okay, it can be aluminium sulfate or aluminium phosphate. Sometimes they add potassium to it, so potassium aluminium sulfate or potassium aluminium phosphate. That's why they call it potash, because of the potassium. Okay, so somebody will tell you that aluminium matoxin have potash. Okay, it is because of the potassium that they added. Ideally, the alum itself is what? The aluminium sulfate. Okay, so the aluminium sulfate is the one that does the linking, that does the bluing. Okay, so you have aluminium sulfate. So when you break aluminium sulfate into two, you have what? Aluminium and then the sulfate. Okay, and the reagent that is used for bluing is an alkaline medium. So I mentioned to you that the hematoxylin is acidic. Okay, even though it is acidic, it stays the acidic component of the cell, which is the nucleus. Okay, and so lipols, as we all know, will not what? Attract. Even if they attract, it will not be solid attraction. Okay, but if you want a solid attraction, then you introduce what? A mordant. Okay, so it is the mordant that is going to hold this positive, this acidic component, hold this acidic component and link them together. So it will stand in the middle. Okay, form a lake, or forms a bridge between the two. Okay, finds a link between the two. Okay, so usually you use the bluing agent should be a solution, alkaline solution at pH 8.0. pH 8.0. MCQ. pH was 8.0. Okay. So what happens? So when you have the pH 8.0, which is alkaline, it's supposed to produce what? OH ions. Okay, it's supposed to produce OH ion. And then when you put, so you have so let's say water, ordinary water. So usually bluing is done with tap water. And tap water is supposed to have a pH of 8.0. Okay, but sometimes you can have tap water that is acidic, okay, or more alkaline, more than 8.0 you cannot use. So you have other tap water substitute. We'll talk about it as we go along. Okay, so when you break down the water into its components, its ionic component, you have H ion and what? OH ion. Okay, and then if you break the aluminum and then the sulfate too, you have the aluminum 3+, and then you have your sulfate, which is 2-. So you have 2 of the aluminum combining with what? 3 of the sulfate to give you what? 6 components, and then they come together to form the aluminum sulfate. Okay, you get me? Great. So when you break it, you form aluminum, which is 3+, and then you form what? The sulfate, which is what? 2-. Okay. And then if you break the water too, you have H ion, which is H1+, and then you have the OH, which is minus. Okay. So when this reaction, we call it redox reaction. If this redox reaction occurs in a solution, what do you think will happen? Aluminum is 3+, OH ion is 1+, sulfate is 2-, OH ion is what? 1+. So which one will follow which? So the sulfate ion will go for the hydrogen. So it will form what? Sulfuric acid. And this sulfuric acid are washed off. That is why bluing is done under what? Running tap water. So when the sulfuric acid is formed, it is washed off, because the sulfuric acid, 1, it will form as a bleach. 2, it will also break again and come and attach to the aluminum and form the original mordant, which will not serve the purpose. Okay, so the bluing is done under running tap water, so that when the sulfuric acid is formed, it is washed off. Okay, then the aluminum will go and bind with what? The OH ion to form what? Aluminum hydroxide. Okay, and aluminum hydroxide is a blue color. Okay, aluminum hydroxide is blue. So the more aluminum hydroxide is formed, the more blue, and then the darker the nucleus becomes. Okay, so that is what causes the bluing. Okay, and that produces what? The blue-black color of the nucleus. Are you okay? Are you okay?
Yes, please.
All right. So any crazy lecturer or examiner can set questions and ask you after bluing what component is formed that produce the blue color. Then it is what? Aluminum hydroxide. Okay. Or what happens during bluing? This one forms aluminum hydroxide, forms sulfuric acid, forms this one, forms this one. So you choose the best one. Okay. So if sulfuric acid is there, aluminum hydroxide will not be there. If aluminum hydroxide is there, sulfuric acid will not be there. One of them. Because unless it is true or false. If it's true or false, then all of them can be there. And then you select the true for the true ones and the false for the false. So this is what I was trying to explain to you. So you have the aluminum hydroxide, which is blue in color. Okay. Then you have the sulfuric acid, which is usually washed off. Usually, if it stays, it will become red. And we don't need red because the eosin is also pinkish red. So you don't need that one. So that one is washed off. And then aluminum hydroxide stays. Okay. So apart from the tap water, I mentioned to you that we also have some alkaline substitute. Okay. So don't forget, I said the pH of the bluing agent was 8.0. Okay, that one is constant. Okay. Or you can get maybe 7.8 or 8.2. So between 7.8 and 8.2, okay. So if you go in the lecture, the examiner doesn't put 8.0, the person puts 7.8, you can take, or 8.2 you can take. But if 8 is there, please take the 8. because that is the ideal pH. Okay. So apart from the tap water, which can be used, there are other also substitutes which can also be used as a bluing agent. Okay, so you have Scotch tap water. Okay, you have lithium carbonate or saturated lithium carbonate, and then you have ammonia water. Okay, ammonia water or ammonia in distilled water is the same. So if you see ammonia water or ammonia in distilled water, it's the same thing. Okay, if you see lithium carbonate or saturated lithium carbonate, it is the same. Okay. And then Scotch tap water. Any of these can be used for bluing. The lithium carbonate, this one's the Scotch tap water is very fast. It's very good. You just a few seconds, then it has started bluing already. It's not like the tap water that you have to do sometime before, because usually it is not 8. It is either 7.8, 8.2. But if you get it, the 8 is fast. So I've spoken about this thing already, the types of alum hematoxylin already. And then I mentioned to you that the more the hematoxylin stays in the sun or is exposed to the sun, the more ripened it becomes. So the longer the hematoxylin stays on the bench, the more effective or the more staining potency it has. Okay, the more staining potency it has. It's not like the chemical ripening, the natural one. That is why they put it in a dark container, because it has been, especially the commercially prepared one, the one that they sell, they are usually in a dark container because they have wrapped they put it in a dark container so that it doesn't, the sun rays it will crystallize. Okay, it will crystallize. And if it crystallizes, it means that the staining component is the one that has crystallized. And so you come and filter it out, and you will not be able to supposed to get it. So these are the years where these hematoxylins were found. Okay, you can take a picture of it. So each hematoxylin, alum hematoxylin, and then the components components. So the hematoxylin itself, you have the alum, you have the water, you have the acetic acid, you have what absolute alcohol, you have this. And then when do you use it? It's a nuclear state. Okay, it's a nuclear state, but if you have some of these components there, it can also stain them tinge of blue black. So even though it is ripened naturally, if you want to use it quickly, then you can add the chemical, because the chemical there, the moment the chemical dissolves, it is ripened already. Okay, so because the ripening takes several months to ripen. Okay, several weeks to ripen. So you can add sodium iodide, which is one of the chemicals that are used to ripen them. And then you have Meyer's hematoxylin. You use sodium iodide as the chemical for the ripening. Okay. And then you have Delafield's, which is natural. Okay, so these are the components. You should take note of the components in case it comes, any of them comes. Then you know what to do. So this is uses the Delafield's uses what? Ammonium alum. the LH uses what? Potassium alum. Okay, so those ones can come in MCQs. Okay, so what is the mordant in LH? Is potassium what? Alum. In Delafius is what? Ammonium alum. In Meyers, it is either ammonium or what? Potassium alum. Take note of those things. Okay, those are the things that can come in your exam. And they are all nuclear steam. And then Harris hematoxylin, you use what? Mercury chloride as the what? The ripening agent. Okay, mercury chloride as the ripening agent. You can take pictures of this one, but these are MCQs. These are the ones that can come in your MCQs. Okay, and then for Coles hematoxylin, the oxidizer is what? Alcoholic iodine. Okay, but the mordant is what? Potassium alum. Okay, in the Harris hematoxylin, it can be potassium alum, it can be mercury oxide, or it can be what? Sodium iodide. You can use any of them. And they are all for what? Nuclear. Okay. And then kerosene are there. Take a picture of this one too. We have potassium iodide as the oxidizer for the kerosene. Okay, and then you have Gills, you have what? Sodium iodide. Okay, okay. And then the sodium, and then you have the aluminum sulfate. Okay. And then for the kerosene, you have potassium alum. Okay, potash. Take note. So what are some of the factors that influences the staining times? I mentioned to you, I've mentioned some already to you. That depends on the age of the stain. How old is the stain? How frequently it has been used, intensity of use of stain. Okay, intensity of use of stain. Okay, the type of hematoxylin that you are going to use also influences the time that you are going to stain. So the time that you use for let's say Harris hematoxylin will not be the same time for you use for LH hematoxylin or Meyers hematoxylin. So all these things will have to be taken into consideration. And also whether you are staining it progressively or you are staining it regressively, all will influence your time that you spend in the hematoxylin. So, and then also pre-treatment. What tissue, what fixative did you use to fix the tissue? Okay, the fixative you use to fix the tissue also influences what? The staining time. Okay, if the tissue was a calcified tissue and you decalcify, decalcification, we use acid. Okay, and acids are what? Bleach. They can bleach. Okay, they can cause all sorts of this thing. So you will treat them separately. So you increase the time if you use decalcification. Okay. Okay. So whether the tissue is also paraffin embedded or it is frozen section will also influence the length of time it stays in the tissue. Okay. And then post-treatment, what are you going to use the tissue for? After staining with HME, or what type of staining are you going to do subsequent? Are you going to do special stain? Which special stain are you going to use? Okay, what tissue or what component of the tissue are you going to demonstrate? All will influence what your staining time. Okay, and then the personal preference, the person who is going to do the staining, you will also decide that you think that at this specific time, the staining characteristics is ideal for you. Okay, so the personal preference too is there. Okay, so these are general rules. If the tissue is frozen, it means that there is no cross-linking, there is no chemical to prevent the exposure of the tissue or anything. So it takes short time to stain. Okay, but if it is decalcified, as I mentioned, it will take longer time because of the acid that you use. Okay, and then if it's formalin fixed, it will also take longer compared to frozen sections, which has not been fixed at all. Okay, sometimes frozen section you use formalin vapor. It is not as you are using the perfect formalin, the fluid formalin. The effect is not as much as that of the fluid formalin. So it means that when you are using alum hematoxylin and you are going to do other staining, you have to be careful. So like Van Giesen, okay. So Van Giesen, if you are using alum hematoxylin, it will not stain well. So usually you use iron hematoxylin. So you use bucket hematoxylin. Okay. So you don't use the normal alum hematoxylin for Van Giesen. So usually when in special stains, you use hematoxylin as a counter stain. Okay, it's not like H&E that the nuclear stain is hematoxylin, and they use the eosin as a counter stain, which stains the cytoplasm. In the case of special stains, the hematoxylin used is a counter stain because you are going to stain component of the cytoplasm or the connective tissue. That is where you use the special stain. So special stains are used for component of the cytoplasm or the connective tissue. Okay, and so you would want to differentiate, or you would want a contrast between the nucleus and then the cytoplasm and then the connective tissue. So if the material is found in the cytoplasm, the nucleus will be stained with the hematoxylin. And so you'll be able to tell that, okay, this is the nucleus. And so the component is found in the cytoplasm, or it is found in what? The connective tissue. Okay. So in special stains, the hematoxylin used is what? Is a counter stain. It is not a primary stain like in H&E. Okay. Okay. So as I mentioned, alum in Van Giesen is not good. So you have to use iron hematoxylin. That's the stated use of Waget hematoxylin. Okay. And then sometimes too, if the component is staining like pinkish or orangish, you also want to have some contrast. So you don't want only the nucleus. So you can do the nucleus, which is the hematoxylin, and then you can also use other color that is different from the original color. Okay, so you can use, if it is pinkish background stain, you can use blue backgrounds, blue counter stain for the cytoplasm. Okay, so the component that you're interested in will stain the pinkish color, and then the blue will be the surrounding, so it stands out, and then you're able to see whatever. Okay, just like you are doing ZN. You see, ZN, the acid fast will stay red, and you want the contrast, so you use either a green background or a blue background. Okay. So this is the protocol for staining with alum hematoxylin. So you do wax. So after sectioning, you have embedded the tissue, so the wax. Wax is not permeable to alum. Alum hematoxylin are usually aqueous. They are water-based. Okay, and so water cannot penetrate wax, and so you have to do wax it. And then you hydrate. You introduce water gradually. Depends on how fragile the tissue is. So you can start as low as 30% alcohol. Then you go to what? Ascending grades of alcohol. Okay. So in staining, in tissue processing, you go through what? You go through what? Ascending grade of alcohol. So in tissue processing, you go through 70 to what? Or 30, 50, 70, 80, 90, then you go to absolute. But in H&E staining, you go through what? Descending grades of alcohol. Please get the two. Descending grades of alcohol in staining and ascending grades of alcohol in processing. Okay, you get the two grades. So for staining, you go from the xylene, which is used for dewaxing, you go to 100% because xylene is not miscible with water. So you don't need, you can't introduce water because it will not work. Okay, so you go to 99.98 or something. Okay, so you go for absolute alcohol. Okay, 2, that is miscible with. From there, from changes of alcohol, you can have 2 or 3 changes, depends on the pockets of the lab, the economy of the lab. Okay, you can have 2. Will completely be removed. Okay, then you go through the descending grades of alcohol. So you can go to 95 or 90, then you go to 80, then you go to what? Depends on what the type of tissue that you are dealing with. Okay, so some of them you have to introduce water gradually. Okay, some of them too after 70% of the taking the testing descending grade of alcohol is the same as dewaxing, hydrating. You stain with the nuclear state. Okay, you stain with the nuclear state. And then if it is regressive, you will differentiate with what? 1% acid alcohol or 0.5% acid alcohol. But if it is progressive, you do not differentiate. You do not decolorize. In progressive staining, you don't decolorize. MCQ. You don't use acid alcohol in progressive staining. You only use acid alcohol in regressive staining. Regressive, you use acid alcohol because you stain it for a longer time and you want to remove excess stain. But progressive, when you have predetermined time, you have specific time, you don't what? Differentiate. But in all cases, whether it's progressive or it is regressive, you will blue. Okay, you bluing applies to all because of the mordant. Okay, because it's alone hemotoxin. But differentiation or decolorization occurs only in regressive staining. Okay, regressive staining. Okay, so you blue, then you counter stain with your eosin, you dehydrate, because after that you are going to clear and then mount. So dehydrate, remove the water, and then you would clear and then mount. So eosin. So we said that the routine stain that we use in hematoxylin and H&E is hematoxylin and eosin. Okay, so hematoxylin is talking about the alum hematoxylin, and then we are talking about the eosin component. So there are 3 types of eosin that is available, and as I mentioned, eosin is synthetic dye. It is produced in the lab, but hematoxylin is a natural dye. It is produced from what? A wood called what? Hematoxylon campanianum. Okay, that one I know you know already. Maybe you might have forgotten that. A logbook, they use the what? The stem. They cut it into pieces, and they put it in water, boil it, and then it impacts its color. And then it is what? Oxidized to hematine, and then it is used. Okay, in the presence of what? A mortar. So now the eosin. So the eosin are xanthine dyes. Okay, they are produced in the lab. There are 3 forms that are produced. You have the eosin Y, which is the most commonly used one across the world. Okay, then you have the ethyl eosin. Okay, the ethyl eosin. Then you also have eosin B. So eosin Y means that it is eosin that is yellow. Okay, eosin B means that it's eosin that is blue. So instead of producing pinkish, it will produce shades of blue. This one, the Y will produce shades of yellow, and then pinkish shades of yellow, and then we have the shades of pink, and then we have the ethyl eosin, which is usually alcohol. We use alcohol to, but the using one, you can use alcohol. So just as I mentioned, okay, so usually it is used as a percentage of 0.5 to 1%. Okay. And then you add a little acid alcohol to make the using the pinkish come out very nice. So ethyl alcohol as I mentioned, alcohol. And then using B, I mentioned to that it is bluish. It has a bluish component. Using wine has a yellow component. So aside EOSM, you can also use any color that can produce a contrast between the nucleus and the cytoplasm. Okay, but it has to be bright, like it has to be pinkish or reddish. Okay, so you can use fluorescent, which is red. You can use barbaric scarlet, which is also red. Okay, so that's the nucleus will be blue-black, and then the cytoplasm and its connective tissue will be what? Red. So it will create a good contrast between them. So some of the eosine are also the water soluble. Those that are aqueous are water soluble. So when you wash it in water, it will easily go. Just like the eosine in Gimsa. The eosine in Gimsa is also water soluble. And so if you have noticed that those who are practicing, you notice that when you wash a BF or Gimsa stain for a long time, or you wash it more, the stain becomes more blue. Like the dye, the stain becomes more blue. And when you look at you are doing whatever you are using the smear for, you see that the nuclear will stain blue. Everything will be blue because you wash it too much in the water. Okay, so when you are using Gimsa, you don't wash it too much in water because the eosine component of the Gimsa that will give it the purple color will be what? Washed off. So everything will be blue. You will not see the purple. It will be blue. So you don't stay in water for a very long time. That is why anytime you are staining, you have to monitor your staining with what? A microscope. So you wash it, you dip 1-2 dips, then you go and check and see whether you are washing off your eosine or it is still there. Okay, you don't have to wash in eosine in tap water for 5 minutes. Just a few dips, at maximum 10 dips, it will give you the best this purplish color. But if you wash it, some of them will even wash it under running tap water, and by the time you finish, everything has become blue. Okay, so you do that. Okay, if it is alcoholic eosine too, it means that it's soluble in alcohol. So you don't what? Differentiate in alcohol. You don't wash it in alcohol. Okay, that is why if it is aqueous, you use aqueous to wash. If it's alcoholic, you use what? Alcohol to wash. So when you stain with hematoxylin and eosine, this is what you see. So the nucleus, okay, the nucleus, which is the DNA, will stain blue-black, okay, blue-black. And then if you have a lot of these macromolecules in the cytoplasm, you have a lot of RNA in the cytoplasm because it's also coming from the DNA. It is not in the, it will pick a bit of the nuclear state, so it will be a bit darker compared to the pinkish side. The cytoplasm will stain shades of pink. Muscle fibers will also stain shades of pink. RBCs will stain shades of pink, orange or pink, fibrate. So anything that is in the, not the nucleus, anything outside the nucleus will stain what? Shades of pink or blue or orange, not blue, shades of pink or red or orange, depends on how you see colors. So I mentioned to you that the other hematoxylins, so we are done with alum hematoxylin. The other hematoxylins are used for special stains, okay? Are used for special stains. So when you want to do special identification of special materials within the cell. So apart from the nucleus and the cytoplasm, there is some intracellular accumulations or some materials in the connective tissue, extracellular matrix that you want to identify. You want to identify muscles, you want to identify collagen fibers, you want to identify elastic fibers, you want to identify other fibers, other materials that are there. Somebody's pathology may just be the fact that the person has too much iron in the body. So when he has too much iron in the body, it will stay in the cell or it will stay in the connective tissue and causing problems for you. So you can have diseases, if we call it hemochromatosis, okay? So you can have diseases associated with too much iron, diseases associated with too much calcium, and you do special things to identify these things, okay? And then when you do those special things, you use these special hematoxins, okay? Sometimes you can use alum hematoxin, but in most cases, you use either iron hematoxin or lead hematoxin or tungsten hematoxin or molybdenum hematoxin. Depends on which one will give you the right characteristics that you need. Okay. So you have iron hematoxin. So these are examples of iron hematoxin. They have Weget hematoxin. I've mentioned that. You have hand-in-hand hematoxin for muscle striation, mitochondria, and the rest. And they have Verhoef's hematoxin for elastic fibers. Okay, if you want to identify elastic fibers, you use what? Verhoef's hematoxin. You have Loyer's hematoxin for myelin. Okay, so it depends on what you want to identify. Then you use which hematoxin will be ideal for you. The iron hematoxin, as you all know, when there is ions or what? Oxidize. Okay, the ion oxidize. So if you use iron hematoxin, the tissue it oxidizes fast. Okay, and then it results in the formation of crystals and other things inside it. So these are some of the things that and they are time consuming. It's not like the alum hematoxin that you can easily stain them. This one, they are time consuming. It takes a long time to work on them. So I mentioned to you that when it comes to alum hematoxin, there is bluing, but the other hematoxin, because of the mordant that they use, we don't glue them. But for the alum, because of the aluminum hydroxide that is needed to form the blue color, so you have to glue it. So these are examples of the iron hematoxins and when it is used, okay, and the components. Study them. Sometimes they bring them in the MCQs. And then you have hand-in-hand hematoxin. I've talked about that already when it is used for mitochondria, muscle striation, and all that. And then you have tungsten hematoxin. Tungsten hematoxin is usually used in a special stain we call it PTAH, phosphotungsten alum acid hematoxin. Okay, it's a special stain that. So when we talk about special stains, we'll talk about PTAH. So any hello, any questions? I think we'll end here. It is 6:58. So next week, God willing, we'll exhaust assessment. So next week we'll talk about special. Any questions about our routine? Hello, do I have people around? Any
Yes,
questions?
please.
Yes, please.
No,
Yes,
madam.
please. Yes.
Okay. Any questions? Are you okay?
Yes, please.
So did you get the catch point areas that can come in MCQs? I pointed some of them out for you.
Yes, ma'am. We have screenshot it.
Okay, great. Wonderful. So we'll end here for today, and God willing, next week we'll continue with the special things.
Okay.
Then we'll do immunohistochemistry, then we'll do the cytology. Okay.
All right, ma'am. Thank you.
Thank
All right.
you.
So if you have any questions, please let me know. Okay.
Okay, ma'am.
All right. Good night. See you next week.
Good
All
night.
right. Bye-bye.
Bye.
Bye.
Bye.